Welcome to problem solving session number 8. In this problem solving session, we are going to solve some problems on Jaynes-Cummings model followed by problems from cavity optomechanics. So as a first problem, here in this problem, you are asked to use this unitary transformation to obtain the following form of the Hamiltonian from the Jaynes-Cummings model. And you are asked to discuss the case for dispersive regime when delta is much greater than z. Okay, so this is an important problem and bit tedious and lengthy, but if you do it in a systematic way, you should be able to work it out. And now I'm going to take you through the solution. So the solution goes like this, and please refer to the lecture number 25 where we discuss the Jaynes-Cummings model. The Jaynes-Cummings model we have written in this particular form where h bar omega a dagger a is the energy of the optical photon, and h bar omega atom sigma z plus 1 by 2 is the energy of the two level atom, and s bar z sigma minus a dagger plus sigma plus a is the interaction term, and this is the interaction between the cavity photon and atom. And this Jaynes-Cummings model I can write in this particular form also. Here only thing that I have done is that instead of writing the two level atom energy in this form, I am writing it in a more simpler form where the energy difference between the ground state and the excited energy state is simply h bar omega, and rest of the terms remains the same. Now you have to apply this unitary transformation where delta is the detuning parameter as defined as capital omega minus omega, where capital omega is the resonance frequency of the atom and omega is the frequency corresponding to the micro radiation. Okay, this is what we have. Now let me take a is equal to sigma dagger a minus a dagger, and lambda is a parameter I am taking as z by delta, and then you can use this transform Hamiltonian, and we are not having the time dependent part in here because this transformation, as you can see, is time independent, so that part is not going to be there. And u is equal to, we can write as e to the power lambda a, and e to the power u dagger is going to be e to the power minus lambda a, and this can help you to use the Hausdorff-Becker formula, and this is already, we are quite familiar with this particular formula. Now utilizing this one, we can write the transform Hamiltonian in this form, and you see there are several terms, and because I am considering the dispersive regime, so I am going to take terms up to the second order in z. So because lambda is equal to z by delta, so lambda square would have the term z square, so I am keeping term up to z square only. And then so basically you are ultimately have to work out this commutation relation to find out this transform Hamiltonian. Let us do that systematically. First, let me find out this quantity, commutation between A and the Jaynes-Cummings Hamiltonian. Now the Jaynes-Cummings Hamiltonian has three parts, H1, H2 and H3. H1 is H bar omega A dagger A. H2 is H bar capital omega by 2 sigma z, and H3 is H bar z sigma minus A plus sigma plus A, right? And now let us work out the all these three commutation relation one by one, and it's very straightforward. H1, you can see that you can get, I have shown you all the steps here. If you follow that carefully, you will get this expression for a commutation between AH1, and then for AH2 again you are going to get this expression here, but now here I have to find out the commutation between sigma plus and sigma z, and sigma minus and sigma z. Sigma plus is the atomic raising operator, and that is ket e bra z. This is sigma plus, and sigma z is the z component of the Pauli matrices, right? So sigma z is can be written in this form, because you know that sigma z is basically 1 0 0 minus 1. So in the basis of kz kt, I can write it in this particular form, and from there the commutation between sigma plus sigma z, if you work it out, you are going to get minus 2 sigma plus. Similarly, sigma minus sigma z is going to give you 2 sigma minus. Then using this you can find out what is AH2. The commutation between AH2 can be worked out easily, and you will get this term. Now you have to find out what is the commutation between this operator A with the third term of the Jaynes-Cummings Hamiltonian, that means with the interaction part of the Jaynes-Cummings Hamiltonian. Then you can just follow the steps and you are going to get this expression here. As you can see, this is simply opposite to this one, so therefore it would be twice of h bar 2 times. That's the reason this factor 2 is coming. Then you have to basically work out sigma commutation between sigma plus a and sigma minus a dagger, and if you break it up, then this is what you will get. You have to be careful here. Now I am utilizing the fact that a dagger, I am using this fact that a dagger is equal to 1. From here I can write a dagger as, this is the usual trick I have used in many places. So this is what I'm using, and this is what I have, right? And then you just have to put it there. Now you have to find out this quantity sigma plus. So this is what you are going to have. Then sigma plus sigma minus, and then sigma plus sigma minus minus sigma plus. You have to work out. To do that, sigma plus sigma minus plus sigma plus, if you work it out, and it's very trivially you are going to get that this is nothing but the identity, and the difference between sigma plus sigma minus minus sigma plus is sigma z. And utilizing these two relations, you can get sigma plus sigma minus as, you just have to add these two, then you are going to get 1/2 of I plus sigma z. Now using this, you can have the commutation between A and H3, the third term of the Jaynes-Cummings Hamiltonian. You are going to get this particular expression. Very nicely everything comes up here, and that means you have now found out all the three commutation relations. So you can finally find out the commutation between the operator A and the Jaynes-Cummings Hamiltonian, and if you put all the terms, all the results, then this is what you are going to get. By the way, here I am using the fact that because you have s cross omega and minus s cross omega here, and this term is common, so I have taken into account of the fact that delta is equal to capital omega minus omega. So I have written it as a single term here, and then I have this last term. Okay, now after that I have to find out this second term in the Hausdorff-Baker formula. In fact, the third term is this commutation relation multiplied by this factor lambda square by 2, and lambda is z by lambda. So this is what you are having. Now A is this, and this part already we have worked out, and this part is, it has two parts. One is this part, as you can see, this has two terms, this part and this part. So therefore you are going to get two terms for the commutation relation. Two commutation relation you have to work out, and this is what you are going to get. By the way, we have already worked this out, because you see here we have already we have worked this particular term, as you can see from here. For example, yes, this one, as you see, this you have already worked out. In fact, this one, right, if you take h bar z outside, then this already we worked out. Now here we are having, it is multiplied by this term. I think it is easy to follow. Hopefully all of you are following. You are having, where we're having it, yes. So this minus h bar delta is there, and if you work this, we have already worked this out, and then we can just write down the result here. This is what we have. And this last term we need not have to work out, because it is multiplied by h bar z here, and then outside this it is again multiplied by z by delta square. So it is basically cubic term, z square into z cube, and we are going to keep terms only up to second order in z. So this last term we neglect, and we are going to have this final result as this one. So we have calculated all the terms, and that is going to give me the transform Hamiltonian as this. We are going to have this Hamilton, this already we know, Jaynes-Cummings Hamiltonian. This expression we have worked out, this commutation we have worked out. If we put that and if we do bit of simple algebra, then after doing the algebra, you are going to get the transform Hamiltonian in this particular form. And while doing it in the previous step, here you see this term is there, I by 2 term is also there, but that term is simply a constant term, so it is not going to affect the energy structure, so therefore we can neglect it. And this is the transform Hamiltonian that was required, and we have worked it out successfully. In a circuit QED experiment with Cooper pair box as a two-level system, the transmitted intensity spectra is observed to have two peaks as shown. So here you are given a transmitted intensity versus drive frequency plot, and when there is no Cooper pair box, without the Cooper pair box, that means the Cooper pair box is not coupled to the radiation, that's what it means. Then you are having one single peak of the radiation shown by this red dotted line. But when there is coupling, then there are two peaks is observed, and you are asked to explain the origin of these peaks using the Jaynes-Cummings model. So in a typical circuit QED experiment, the setup is somewhat like this. Here you are having this transmission line resonator, and in the transmission line resonator, near to the resonator, a Cooper pair box is placed, and a microwave radiation is incident on the resonator, microwave resonator, and this microwave can enter into the cavity resonator if it satisfies the cavity resonance condition. That means when delta is equal to 0, the microwave can enter into the resonator. Okay, so this actually we know from our lecture class number 25, where we have discussed about this kind of setup, and in fact we discussed Jaynes-Cummings model in lecture number 25. Please refer to that. Now what we are having is that when this Jaynes-Cummings model we have studied, this is what the energy level structure we obtain when the resonance condition is satisfied. In the presence of the coupling, as you can see, the energy levels are now getting hybridized, and this is the structure. For example, this basically means this lowest energy structure is the ground state, where the atom is in the ground state, or the Cooper pair box is in the ground state if we consider it as a two-level system, and there is no photon, microwave photon in the cavity. Then there may be a one microwave photon in the cavity, but the Cooper pair box still in the ground state, or there is no photon in the cavity, but the Cooper pair box may be in the excited state. But when this coupling is there, then these hybridized energy levels, this energy level KZ1, KE0, they get hybridized, and we are getting two energy level. One energy level has this eigenstate, that is the symmetric superposition of this KZ1 and E0, and the another one is antisymmetric superposition of KZ1 and E0. Now when the microwave photon is entering into the cavity, and initially say the Cooper pair is in the ground state and there is no photon, so initially we are in this energy level in the ground state. Now when a photon is entering into the cavity, then we may be either in this particular state, because this particular state shows that there is a possibility of having one photon in the cavity, or maybe we are in this particular state. So that means that there are two transitions possible. One transition is this transition, and another transition is this two transition. Now if you see these two transitions, the energy level difference between these two transitions is 2 h bar z, or in frequency it is simply 2z. And in fact this is what is the origin of these two peaks in the intensity spectrum that is shown here, and as you can see the frequency difference between the two peak is 2g. So that means that this energy level structure of the offered by the Jaynes-Cummings model very simply explain the origin of these two peaks. Now let us work out this problem number 3 related to quantum optomechanics. Here the optomechanical Hamiltonian is given, and using the unitary transformation you are asked to obtain the transform Hamiltonian. So let's do it, and to do that we are going to use the usual technique of applying the Hausdorff-Baker formula. And you know the transformed Hamiltonian is going to be h tilde is equal to u dagger h u minus I h per u dagger delta u delta t. This is going to be the transformed Hamiltonian, and here u, the unitary operator, is given as e to the power minus I omega l a dagger a t. Okay. So we know the Hausdorff-Baker formula. Let me write it again. E to the power lambda a b e to the power minus lambda a, that is equal to b plus the commutation between a and b multiplied by this parameter, constant parameter lambda, and we have the term lambda square by 2 factorial, commutation between a and commutator ab, and we'll have all higher order terms. Now let us work certain terms first. First let me find out this quantity e to the power I omega l a dagger a t, that's the unitary u dagger, and I have say operator is a e to the power minus I omega l a dagger a t. Let me first work out this. Now by the way, before I do that, let me take lambda is equal to I omega l t, and I will take a is equal to a dagger a and b is equal to a. Then I can put it in the Hausdorff-Baker formula. So let me write that I omega l a dagger a t a e to the power minus I omega l a dagger a t, and this is going to give me first term a plus I omega l t, commutation between a dagger a. All right, then I have I omega l t whole square by 2. Then I have, let me write it in this way. First let me work out this commutator, that is your a and b. Okay, so if I work it out, it's very trivial to work it out. You can see that you are going to get minus I omega l t a. This is going to give you minus a, then you have plus I omega l t whole square by 2, and here you are going to have a dagger a, commutation between a and b is minus a. Okay, and this is going to give you a minus I omega l t a, then you have plus I omega l t whole square by 2, and this is going to give you simply plus a, right? Okay, and then you will have terms like this. So if I take a common, then I have this series 1 minus I omega l t plus I omega l t whole square by 2 factorial minus, and this way you will get this series, and that is nothing but the exponential series. So you can write it as e to the power minus I omega l t. So in the similar way you can find out Similarly, you can find out e to the power I omega L a dagger a t. This time take the operator a dagger and you will get the simple calculation you can do the way I have done it. You are going to get it as a dagger e to the power plus I omega L t. A dagger a. No, actually you will get I omega LT only. Okay, so this is what you are going to get. So please keep these results, remember these results. We are going to utilize it again. However, you have to work out this also. Again, you have to find out u dagger a u. This is very easy to work out. You have I omega L a dagger a t a dagger a u is e to the power minus I omega L a dagger a t. This is going to give you a dagger a plus I omega L t commutation between. Okay, this is very trivial. A dagger a dagger a. This commutation is going to give you 0, and therefore all the higher order terms that you are going to have are also going to be 0. So you will be left out with only a dagger a. So this result is also you have to use. And by the way, very trivially you can get u dagger b u, that is simply going to give you b dagger b. All right, and you also have this particular term u dagger delta u delta t. Let me work it out. U dagger is e to the power I omega L a dagger a t, and if I take the time derivative of delta t, u is minus I omega L a dagger a t. This is going to give you simply minus I omega L a dagger a. Okay, now by the way it was multiplied by I h bar, so let me work that out. I h bar delta u dagger delta u delta t is going to give you h bar omega L a dagger a. So we have all the terms at our disposal. Now collecting all of them, you can write down the transform Hamiltonian as h bar omega 0 a dagger a plus h bar capital omega m b dagger b, okay, minus h bar z a dagger a b plus b dagger, okay, and you have I h bar omega drive. Now here you have a dagger is now going to be replaced by a dagger e to the power earlier. Okay, just again look at this expression here. You have a dagger e to the power minus I omega LT is there, but now as you have seen that when you have done the transformation, a dagger is going to be replaced by a dagger e to the power plus I omega LT. So these two terms is going to get cancelled out. So therefore you will be left out with only you will be having here a dagger minus a, and then from the last term you are going to have minus h cross omega L a dagger a. Now defining the detuning parameter as omega L minus omega 0, you can write the final Hamiltonian, transform Hamiltonian in this form. You are going to have minus h bar delta a dagger a plus h bar omega m b dagger b, okay, minus h bar z a dagger a into b plus b dagger plus I h bar omega drive a dagger minus a. So this is the required Hamiltonian, transform Hamiltonian, and this is what we have written in our lecture classes as well. So, and you have seen that it's, if you do the apply the Hausdorff-Becker formula systematically, you can very easily obtain this result. Now let us work out this problem number 4. Starting with the Hamiltonian, This Hamiltonian just we have worked out. Obtain the linearized optomechanical Hamiltonian. So this is an important problem, and let me do it very systematically. To do this problem, first of all, let me write down the Heisenberg equation of motion using this given Hamiltonian. For the optical mode A, the Heisenberg equation is IH per dA dt, and I have here commutation A and H. And if I apply this to the Hamiltonian, given Hamiltonian, you are going to get here minus H per delta A minus H per capital Z A B plus B dagger, and you will also have plus IH per omega drive. Okay, and this is going to give you A dot is equal to I delta A plus I capital Z A B plus B dagger and omega drive. So this is one equation you will get. And then for the phonon mode, you are again going to get this IH per dB dt is equal to the commutation between B and the Hamiltonian. This is going to give you H per capital omega B, please verify yourself, minus H per Z A dagger A. Okay, and from here you are going to get B dot is equal to minus I capital omega M B plus IZ A dagger A. Okay, these are the equations that you have obtained from Heisenberg equation of motion. So this is the equation you get for phonon mode, and this is the equation you have got for the photon or the optical mode. Now, taking into dissipation and quantum noise into account, I can write down this evolution equation for the modes. A dot I can write as A dot is equal to I delta. Let me actually write here, taking dissipation and quantum noise, dissipation and quantum noise into account, I can write A dot is equal to, I have to just certain terms phenomenologically, I have I delta A plus I Z A B plus B dagger plus omega drive. Okay, this I got from the Heisenberg equation, and then phenomenologically I am going to add this dissipation term. Optical mode is decaying at the rate kappa by 2, and then quantum noise is entering into the optical mode via this expression. So this is what I have for A dot, and for B dot I have minus I omega M B plus IZ A dagger A. Okay, then this I have, up to this I have from Heisenberg equation of motion, and then phenomenologically I have to add this. Phonon mode is decaying at the rate gamma m by 2, this B, and quantum noise is entering via this expression, that is the quantum noise. Quantum input noise is this square root of gamma m B in. Now these are the so-called quantum Langevin equation that we have written here, and as you can see, these quantum Langevin equations are nonlinear, and to linearize this nonlinear equation we are going to adopt this procedure. So we are going to take A as equal to two parts. One is the classical steady state part, alpha bar is the steady state solution, that's the classical part. Then I have this quantum fluctuation delta A. Similarly for B, I have the classical steady state is solution is beta bar plus delta B is the quantum fluctuation. Now if I put these answers A and B in the quantum Langevin equation, for the optical mode I will get delta A dot is equal to I delta alpha bar plus delta A, okay, plus Iz. You just have to do the things methodically and systematically, then you will get the right result. Iz into alpha bar plus delta A, right? I am replacing A with alpha bar plus delta A, and then I have here, you see, I have B plus B dagger. So in B plus B dagger I am having beta plus beta star, okay. Then I have delta B plus delta B dagger. This is what I will have. And then I have omega drive minus kappa by 2. A is now going to be replaced by alpha bar plus delta A, and quantum noise is as it is, square root of kappa A in. Now separating out the classical and the quantum part on both sides, and also ignoring the nonlinear bilinear terms, like you have this product terms delta A, delta B, delta A, delta B dagger, all these terms can be neglected because these are nonlinear terms. Then you separate out the classical part and the quantum part. So let me do it for the classical part first. Classical part, if I compare both sides, on the left hand side there is no classical part, so that is going to be equal to 0. And on the right hand side I am going to have I delta alpha bar plus Iz alpha bar into beta plus beta bar plus beta bar star, okay. This is what I will have. And then I have omega drive, which is also classical, and minus kappa by 2 alpha bar, okay. And quantum part, so quantum part you can compare. If you compare both sides, on the left hand side I have delta A dot, that is equal to I delta A plus Iz capital Z alpha bar. You will have here delta B plus delta B dagger, okay. I have ignored all the nonlinear terms, please note that. And I have Iz delta A beta bar plus beta bar star, okay, minus kappa by 2 delta A minus square root of kappa A in. Alright. Now from the classical part, you see, from the classical part you can immediately get alpha bar. This expression you are going to get, omega drive divided by kappa by 2, okay, minus I delta plus G beta bar plus beta bar star. This is what you will get. And this you can actually write in this form. You can write it as omega drive divided by kappa by 2 minus I delta dash, where delta dash is the modified detuning constant and defined as delta dash is equal to delta plus capital Z beta bar plus beta bar star, okay. So this is what you will have. From quantum part, you are going to get delta A dot is equal to I delta plus Z beta bar plus beta bar star, okay. Then you will have here delta A plus I Z delta B plus delta B dagger minus kappa by 2 delta A minus root over kappa A in. Here I have defined this small z as the linearized optomechanical coupling constant, that is defined as capital Z into alpha bar. Okay, so I'm going to take alpha bar as a real quantity. Anyway, I'll come to that later. So I am now having my delta A dot is equal to I delta dash. Now here you see this quantity is nothing but delta dash, as we have defined it like this: modified detuning parameter minus kappa by 2 delta A plus Iz delta B plus delta B dagger minus root over kappa A in. So this is the equation I obtained for quantum fluctuation of the optical mode. Similarly, from the phonon mode equation, we can obtain delta beta. Let me write similarly. I can get delta B dot is equal to minus I omega m beta bar plus delta B, okay, plus Iz capital Z alpha bar star plus delta A dagger alpha bar plus delta A, okay, and minus gamma m by 2 beta bar plus delta B minus square root of gamma m B in. Okay, separating again the classical and the quantum part and ignoring the nonlinear terms. So let me write here separating classical and quantum parts and ignoring nonlinear terms such as you are going to have this here delta A dagger delta A, this kind of products you have to ignore. Then you are going to get from the classical part you are going to get z, because the on the left hand side classical part is 0, so you are going to have minus I omega m beta bar plus Iz mod alpha bar whole square minus gamma m by 2 beta bar, okay, and from the quantum part you are going to have delta B dot is equal to minus I capital omega m delta B plus Iz alpha bar star delta A, okay, plus I capital Z alpha bar delta A dagger minus gamma m by 2 delta B minus square root of gamma m B in. Now I am defining Z is equal to small z, the optomechanical constant is equal to Z into alpha bar, and also I am taking that alpha bar is equal to alpha bar star. Alpha bar I am taking as a real quantity. Then I can write delta B dot is equal to minus I capital omega m plus gamma m by 2 delta B plus I small z now delta A plus delta A dagger, okay, minus square root of gamma m B in. This is what I am going to have. So you see we have obtained the following evolution equation for quantum fluctuation of optical and phonon mode operators. So let me write them again. Delta A dot I am now getting as I delta dash minus kappa by 2 delta A, okay, plus Iz delta B plus delta B dagger minus square root of kappa A in. And for the phonon mode I have delta B dot is equal to minus I capital omega m plus gamma m by 2 delta b plus Ig delta A plus delta A dagger minus square root of gamma m b in. So these are some equations that we have obtained. These are very important set of equations we obtained here because of the linearization. And please note that here in lecture 28 we wrote the second equation wrongly, because there I have written delta A as delta B and delta A dagger as delta B dagger, which was not correct. Please make that correction. Now, ignoring dissipation and quantum noise, I can write delta A dot is equal to I delta. I am also writing delta dash as delta A plus Ig delta B plus delta B dagger, and delta B dot is equal to minus I capital omega m delta B plus Ig delta A plus delta A dagger. Now we can easily get this set of differential equation using the Hamiltonian. You can get it from this Hamiltonian. H is equal to minus H per delta A dagger delta A plus H per capital omega m delta B dagger delta B minus H per Z delta A plus delta A dagger into delta B plus delta B dagger. And this is what is our linearized optomechanical Hamiltonian, and you can actually very easily verify that you are going to get this set of equation using the Heisenberg equation of motion. Please try to do that. If you use this Hamiltonian and apply the Heisenberg equation of motion for the optical mode and the phonon mode, you will be able to retrieve this set of coupled differential equation. Let us now work out this fifth problem. In this problem, a cavity optomechanical system is given with these following parameters. Mass of the movable mirror is 5 nanogram. Cavity decay rate kappa is 0.04 times the capital omega m. Capital omega m is the resonance frequency of the mechanical oscillator. Capital omega m is 100 megahertz. Length of the cavity is 3 micrometer. The wavelength of the laser is 750 nanometer. Planck's constant is given as 6.626 into 10 to the power minus 34 joule second. You are asked to find the magnitude of the detuning parameter delta, then find the magnitude of 0-point fluctuation of the movable mirror, and then finally you are asked to find the minimum number of thermal quanta to which the movable mirror can be cooled. Okay, let's do it one by one. So first of all, let us find out the detuning parameter, and we know that the detuning parameter delta is defined as omega L minus omega 0. Omega L is the laser frequency and omega 0 is the cavity resonance frequency, and omega L is equal to, we know, 2 pi c divided by lambda, where lambda is the wavelength of the laser. Now let me work it out. 2 pi c is the speed of light, that is 3 into 10 to the power 8 meter per second, and lambda is 750 nanometer, right? That is what is given. Lambda is equal to 750 nanometer. That means it is 750 into 10 to the power minus 9. And if you actually do the maths, omega L, you are going to get it as 2 pi into 4 into 10 to the power 14. Okay, please do it carefully. This is what you should get. And Now let me find out what is the cavity resonance frequency omega 0. We know the resonance condition for a given mode, that is omega 0 is equal to pi into c divided by the length of the cavity. So c is 3 into 10 to the power 8. L is equal to 3 micrometer. That means 3 into 10 to the power minus 6 meter. So this gives me pi into 10 to the power 14. So this gives me delta detuning parameter omega L minus omega 0 is equal to 7 pi into 10 to the power 14 hertz. This I can write in a more neat form. I can write it as 2 pi into 350 terahertz. So this is my detuning parameter, 2 pi times 350 terahertz, and you know 1 terahertz is equal to 10 to the power 12 hertz. Now let us do the second part of the problem. In the second part of the problem, you are asked to find out the magnitude of the 0-point fluctuation of the movable mirror, and we know that the 0-point fluctuation of the movable mirror is given by this formula. It is square root of h bar divided by twice into m into capital omega m. All the parameters are given. So first let me find out what is h bar divided by twice m omega m. H bar is h divided by 2 pi, so I can write it as 4 pi m into capital omega m. And now if I put h is equal to 6.626 into 10 to the power minus 34, and then 4 pi into mass is given to be 5 nanogram, right? Let us see again. Mass is given as 5 nanogram. So it is going to be 5 times 10 to the power minus 9 gram, but I have to write it in kilograms. So then I have to put another minus 3, 10 to the power minus 3, this much of gram, and omega m is 100 megahertz. That is what is given. So let us confirm once again. Yes, you are given omega m to be 100 megahertz. So therefore you have to write here 100 into 10 to the power 6. So this way, if you do the maths here, you are going to get it to be 6.626 divided by 62.8 into 10 to the power minus 30. So if I take the square root, then I get the 0-point fluctuation as, I will get it as h bar divided by twice m omega m, right? If I take the square root of the above magnitude, I am going to get it to be around 3.2 into 10 to the power minus 16 meter. So that's the 0-point fluctuation I obtained. Now in the final part of the problem, you are asked to find the minimum number of thermal quanta to which the movable mirror can be cooled, and we have discussed this issue when we have discussed ground state cooling. We found that the quantum limit for cooling is given by this formula. This is the minimum number of thermal quanta which can be achieved if you do the ground state cooling. The formula was kappa divided by 4 times capital omega m whole square. Now in the given problem, it is given that kappa is equal to 0.04 into omega m. So it implies this ratio of kappa by capital omega m is 0.04. So putting this in the formula, you are going to get minimum number of thermal quanta is going to be 0.04 divided by 4 whole square, and this gives you simply 10 to the power minus 4. So this much number of quanta, average number of thermal quanta you can achieve. This is basically the limit you get. Thank you so much.